So when we look at how many primes there are in the universe, right, there's two possibilities. There's either a finite number of primes or an infinite number of primes. Okay, so there's only two possibilities. So if I were able to eliminate one of those possibilities, then the other possibility would be all that remains. And that's actually the basis of this proof. So with this proof, I don't even want you to write anything down in this section. I just want you to listen. Okay, but we're going to use this method called proof by contradiction, and it might not fall on your ears quite right at first. You might feel like this sounds illogical, but this is actually a tactic used a great deal in upper level math to prove things that are difficult to prove, right? Because how could I really prove there's an infinite number of primes? How could I prove anything about infinity, right? But the way that I prove that is I say, well, it's either finite or infinite, right? That's all that's possible. And if I can say, well, I tried letting the number of primes be finite, I ran into a problem, therefore this can't happen, then that's all that I'm left with. All right, and so that's the basis of this proof, is we're going to say there's an infinite number of primes because there can't be a finite number of primes. So before we get started, this fact, and we actually ran into this fact earlier today when we were testing to see if large numbers were prime. All right, and we noticed that if a prime wouldn't divide the number, no multiple of the prime could divide the number either. All right, and so that's how we got that shortcut of saying, well, if we want to test to see if a big number is prime, we only have to test prime divisors, right? Because if 2 doesn't divide a number, no multiple of 2 will divide the number either, right? And if 3 can't divide the number, no multiple of 3 is going to divide the number. So we only have to, when testing for possible divisors, we only have to check and see if prime numbers will divide it. So that's a fact that's going to help us here. So basis of the proof, as I just said, there's an infinite number of primes because there can't be a finite number of primes. All right, so suppose then that I said, well, I think there can be a finite number of primes. And if they're finite, then I can list them all. Okay, so if I were to say there's a finite number of primes, there's n primes, and that's all that live in the universe, right? Is I have some number n, and that's how many primes I have, and then that's it. All right, so if the number of primes was finite, I'd be able to list them all out. So I'd have prime 1, prime 2, prime 3, prime 4, prime 5, up to prime n, right? That's the full list of primes. And then if I assume that this is all the primes that there are in the universe, I'm going to define this new number where I take all of these primes and I multiply them together. Okay, because I have this finite list, and I'm going to put dot, 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 and I'm going to call this the kth prime, right? And then I'm going to put dot, 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 dot again, and I'm multiplying this together with the nth prime. So I've taken every number in that list, I've multiplied it together, and then I'm going to add 1 to that. All right, and so I have this new number, right? And so any number greater than or equal to 2 is either prime or composite. All right, so I have to consider, is this number a prime, or is this number composite? Okay, and again, there's only two possibilities. Any number greater than or equal to 2, any whole number is either prime or composite. Well, I said I listed all the primes, right? So then if I tried to say, oh, well then this number must be prime, I would have already contradicted myself, because if this number is prime, it would have already had to have been in my list, right? But it's not in my list because I formed it by multiplying every number in my list and adding 1. All right, so I've eliminated the possibility that this number is prime. Otherwise, I've already contradicted myself. All right, so then I say, oh, okay, well then if it's not prime, it's composite. And if it's composite, it has to have a prime divisor, meaning some prime in this list had to divide it. All right, so let's say, I don't know which prime it is that's going to divide it, but I'll call the prime that does divide it P sub k. Okay, because some arbitrary prime in that list had to divide this number. All right, and then here's where I run into a problem. All right, so let me just come over to the side and talk about how we divide in this situation. All right, if I were doing 6 plus 9 and I wanted to divide that by 3, right? And all of you would say, well, that's just 15 divided by 3, that's just 5. But when I divide in this form, I have to divide into each addend in the sum, right? Because dividing by 3 is multiplying by a third. And so if I use the distributive property and multiplication distributes over addition, I can see that I would have to take a third of each of these numbers. Okay, so what that tells me then is, applying this same principle here, P sub k would have to divide this part, which is no problem, right? Like, of course, P sub k would divide this, right? Here's a P sub k, these would cancel, right? But then the problem is P sub k would also have to divide 1, right? So I would need 1 to be divisible by P sub k. Okay, so I'm just going to write that in the text box, even though I told you didn't even have to take notes. But just to clarify, the only way this works is if P sub k divides 1, right? But nothing divides 1, right? So then I've run into a problem, right? So I already said this number can't be prime. Well, then I notice this number can't be composite either, right? Well, then that means this full list of primes, this finite list of primes, that can't happen, right? Well, if the list of primes can't be finite, then all I'm left with is it's got to be infinite. Okay, so the number of primes is infinite because when I tried saying it was finite, I ran into a problem. Okay, so the list of primes is infinite because it can't not be. Okay, so let me just say that one more time. The list of primes is infinite because it can't not be. All right, and some people don't like that logic, but that's actually a very valuable tool used in upper level math to prove things.